Good day, everyone. Today, we are getting further into regression. Our objective is to create and analyze regression equations, and these equations are linear, quadratic, and exponential. Last class period, we got ourselves introduced to creating the models. So, I know I don't have a video posted for that, but if you are still struggling to know how to create regression models, I will have supplemental videos for you to understand. Alright, remember this. Numbers are so powerful that they can define you, they can help you survive, they can hinder you, and also they could be used as a weapon, worse than rumors. I prefer to be people say bad things about me behind my back than people talk bad about me and use numbers to talk trash about me. That's the worst experience, horrible. As you guys are aware, you students are defined by your grades, as I am defined by my test scores with you. Alright, we're going to get back to that momentarily, but let's get into our precise definition of mathematics, because again, you gotta know this definition. You must know it. You have to know it. Alright, the precise definition of mathematics is the technique to explain, understand, and deal with reality by ciphering, counting, measuring, classifying, ordering, inferring, and modeling patterns arising in the environment. Yeah, it is imperative for us to know each part of this definition. We must know it. So what we may end up doing next class period or what have you, we're going to define each piece of it. So what does it mean for me to explain? So we know that explain means to teach. Understand means you listening and you know what's going on. To deal with, manage. When you're dealing with somebody, you're managing them, right? Cipher means to decode, count, try to figure out a specific amount, But we're also going to define counting a little bit more too, because I need for you to understand what does it mean to truly count. Measuring, measuring and classifying do sound the same, but they are a little bit different. You're measuring something in terms of something. Classifying, you put it in a particular group. Ordering or whatnot is different from classifying, because ordering, you could go from the smallest to the largest. Classifying, you're just putting them in groups. Inferring means to just make a conclusion based on the facts that are given to you. In our community, we jump to conclusions a lot, and we do that because if someone talks some way, we think they're weird. That's just the inference we get. And modeling patterns, what we're going to do today, arising in the environment. Announcement. All right, I'm going to make it rain. I'm going to make it rain in this grade book. But to do that, you got to go hard. You really got to be all about it. Be focused and go hard. Homework completion will set you free, y'all. Promise y'all. To get out Algebra 2, that homework got to be done. If it can't be done, I can't help you. And the results. Remember how I told you that I, as your teacher, is defined by numbers too, just like you are by your grades, and me, your results? This is how I'm defined by it. So this is the results of what we did the third 9 weeks. So 40% to 33%. For the second 9 weeks, 21% to 18%. And for the first 9 weeks, 39 to 36. What can I say about that? I can say that People say that I'm a good teacher because of those results. See, they're not defined about me, Theodore Howard. They're more interested by my numbers. They don't care about me as the person. Just like most you try to go to college, they don't care about who you are as a person. They care about your grades. And you try to get that money from the colleges. All right, correlation. We tell about this. Correlation really talks about the relationship. There's a relationship between two variables. All right. Correlated variables do change together. Correlations are sometimes called trends. We are dealing with polynomial and non-polynomial trends, and we're going to get to that a little bit later. Perhaps not in this lesson, but in some future lessons. In English, this just means cause and effect. So when you have your data scattered around like that, there's just no relationship. So yeah, let's look at this relationship. So splash of the slide water park attendance, high temperatures and admission tickets sold. So we see a strong positive relationship. So that just means that as the daily high temperature increases, the number of admission tickets also increase because the hotter you get, the more tickets sold. So that's a strong relationship. Does it necessarily make sense? Well, it does, but it's very logical to most people, but you good on this. The correlation is strong because all the points fall close to a line. So when the points form a shape, guess what? It's a strong correlation. Now, just because two variables are correlated does not necessarily mean that there are variables cause the other. So basically, if it's correlation, it's a relationship. But that doesn't mean that the relationship is a cause and effect. When it's a cause and effect, it's a causation. All right? So sometimes when things are a coincidence, we have to do more research. And we're going to deal with 3 examples. So, before we dig into this, sorry about that, y'all. Need a little water break. So, you have a situation about graphs, right? So when you have points that, like I told you, come close together with r equals 1, that means that it forms a perfect historical correlation. So that means that there is a strong relationship. But again, that does not mean even and odd. It does not mean, it does not mean a cause and effect. So when r is -1, you still got a strong relationship, but it's a strong negative relationship. Like a scenario could be the more disruptions I have in my classroom, the more zeros I give. Your grade decrease, which is true. Because in my classroom, you can't be disrupting no one. When you do that, your grades do decrease. So that's one relationship, which is a negative, strong relationship. But here's a converse of this. When you turn in the work, your grade increase. So that's a positive, strong relationship. So all these right here, again, when you have dots that are not forming a shape, like when r equals 0, that means you don't have a relationship. So there's no correlation there. And remember, correlation is defined by the letter R. So when you see the 0.66, it's not forming the line because it's a little scattered, but when you look at 0.95, it almost formed that perfect line. All right? If you have any questions about that, just see me, and I could just draw markers there. Unfortunately, I don't have the technology at the moment to draw the lines for you to see what I'm talking about. All right. So here's an example. When the restaurant has more customers, there's less light outside. So remember, there's a relationship between the two, but doesn't mean it's a cause and effect. So the cause being that the restaurant has more customers, and the effect is the light. Or you can look at that conversely if you want to. There's less light outside, so more customers. Is that proper cause and effect? No, it's not. It's not a proper cause and effect. So when you have that going on, that means that you have to research as to why do the restaurant have more customers when there's less light outside. It could be, well, they just got through having a tailgate party from having a little bit of a party after the game. It could be more reasons like that, or a birthday party. So let's look at the second one. When the weather is snowier, stores sell more baking supplies. That's not a proper cause and effect either, because just because it's snow outside does not mean that we're going to be going to the store and go baking. Most people usually, when it snows, they stay inside. Cause and effect. Or if you are in the South, that is. When the weather is snowier, stores sell more wrapping paper. Not a proper cause and effect. But if we do some research to it, it's probably because of Christmas. So again, just because you see a statement that's correlated, like the three statements we see here, does not mean that there are a proper cause of effect to each other. All right? So a question, which one of these relationships reflects a correlation? Which relationship most likely reflects both correlation and causation? Causation again is cause and effect. A proper cause and effect. So A, burning more candles is associated with having a better smelling room. B, burning candles is associated with having a tidier room. Or C, burning more candles is associated with listening to soothing music more often. I would say the answer is to be A, because when you're burning more candles, there's a better smelling room. We could all agree to that. That's a proper cause and effect. You know? B cannot be a proper cause and effect. It's a correlation, no doubt. All of them are correlation, but B is not a cause and effect because burning more candles does not mean that your room is more tidier. That's not always the case. C, burning more candles associated with listening to soothing music more often. I almost went with C, but hear me out. It's not a proper cause and effect. Again, people who burn candles doesn't necessarily mean that they listen to soothing music. They may just be chilling on the couch watching TV, you know? So, you know, you may see your parents light a candle and they may be snugged up watching TV while you bothering them. So, that's the reason why A is the proper correlation and cause and effect. Alright, so how does correlation and causation satisfy the precise definition of mathematics? Remember, we have to know the precise definition of mathematics and put the pieces together. We have to use it accordingly. So, the technique to explain, understand, and deal with reality by inferring. We made inferences the whole time, right? So we looked at those scenarios and we tried to, see can we make an inference of is there a cause and effect. We didn't count, we didn't measure, we didn't classify. You almost could say that, but we didn't classify. You know, what? If you said classify, how did you do it? you mainly did it by a friend. So I guess you could say classify, but the main thing you did was you inferred. So inferring is what you did. But if you was to say classify, I give you some credit, but I won't give you full credit. All right, so let's get back to correlation. So y'all remember, correlation is between -1 and +1. So when two variables have a correlation coefficient of 1, which is r, then there is a perfect positive correlation. So that means that all the dots together form a perfect shape. Doesn't necessarily mean we're going to have a perfect line. We're probably going to have a curve, you know, for the exponential and the quadratic. What about if it's -1? That means there's a perfect negative correlation. So that means that the graph's going to be decreasing because it's negative. And that's when all your points come together still and they form a perfect shape. So when it's not 1 or -1, that means that the relationship, the correlation is not going to be perfect or strong. So if it's 0, that means that all the points scattered away, as you have seen in this video earlier, all the points just running away. So keep in mind about that, right? So the further away from 1 that they are, the more scattered they get. The farther they're away from 1 and -1, the farther away they get. So all I'm saying is, again, when the points are away from -1 or +1, they scatter. When the points are away from -1 and 1, they scatter. When the points are away from -1 and 1, they scatter. When the points are away from -1 and 1, they scatter. Good, I think you got me by now. And this is what I'm talking about. You saw this again. So the point 0.66 is not close to 1 as is 0.95. 0.95, they're almost forming a shape. But see, 0.66, they're a little bit scattered. But when it's 0, again, where r is 0, the correlation is 0, they scatter all over the place. So again, the further they're away from -1 and 1, the more scattered they get. Again, when the dots are further away from -1 than 1, the more scattered they get. So when the dots are away from -1 or +1, the more scattered they become. Alright, like here at -0.49, they're becoming more scattered here. So you're +0.66 because it's closer to +1. They form a little bit of a shape. Here, they form a somewhat of a shape, but they're still scattered. And -0.97, this is close. This is almost to a perfect line. All right. I think we're good. So let's move on. So example, match. When r is +1, which one should it go to? When r is 0.2, which one does it go to? Well, because r is -1, not 1, it's a perfect correlation. So that means that all the dots are forming a line. So the -1 is the first one, 0.2, because it's far away from +1. Guess what? The points are more scattered. Alright, so again, as I told you guys, regression is between 1 and -1. This stuff that you see on the screen is not really of importance, but unless we're dealing with slope, which we would be, but you don't need to know all this. So this is not needed. But the first line, again, we're not doing just linear regression, we are doing quadratic and exponential regression. It's an approach to modeling the relationship between a dependent variable, y, or one or more independent variable denoted as x. So what I just said about the regression piece is important. All this other stuff is not. Oh, here. In the regression line equation, x and y are the variables of interest in our data. So we care about x and y. So that's very true. The unknown, the dependent variable, and the x known or independent variable. All right. So again, we already know how to put stuff into decimals by now. So we have to figure out when we put a table, how do we know it's going to be linear, quadratic, or exponential? Remember, you're going to be looking for the R. All right? You're looking for the R. The R is your correlation. So when it's a linear, we are concerned about the small r. We're not worried about the big R, the small r. The small r is the correlation. All right? So when you're dealing with the quadratic, you are worried about the r squared. That is the correlation for the quadratic. So when you're dealing with a exponential, you are also worried about the r squared. So you're trying to look at the r for linear, and for the quadratic exponential, you can look for the r squared. Well, truthfully, if you want to be fair, you could look at the r squared too if you want to. The r squared could help us out also. So for the linear, just look at both of the r's, because they're both pretty much, there's the correlation, they're all correlations. So you're okay with looking at both of those. So the r for the linear is 99, and for the r squared 98. So for the quadratic, r is 1. And then for the exponential is 98. So 199 if you round it, that is. Keep in mind, you're looking for which one gives you the most perfect correlation. If it does give you the perfect correlation, which one comes close to the perfect correlation? And when you look at that, you realize it's going to be quadratic. The quadratic, because r squared equals 1, gives you the perfect correlation. So that means that you're going to have all the points going to form a shape, and almost all of them is going to touch the line. So there you are. It is quadratic. And of course, the negative 7 is my a x squared. All right. All right, y'all. Let's get ourselves back to it. All right. Good. We're good. Now, let's talk about what's the point of a regression. A regression analysis is the process of building a model of the relationship between variables in the form of mathematical equations. The general purpose is to explain how one variable, the dependent variable, is systematically related to the values of one or more independent variables. And that's when we're dealing with quadratics and exponentials. An independent variable is so called because we imagine its values vary freely across its range, while the dependent variable is dependent upon the values taken for the independent. So going back to middle school, you know that x is independent by its dependent. The mathematical function is expressed in the terms of the coefficients of the equations and the value of the independent variable. The coefficients are numeric. Remember, you worry about the coefficients. Numeric constants by which variables' values in the equations are multiplied or which are added to the value to determine the unknown. So it's mainly X and Y, input, output. So here's the situation that you're going to be dealing with. So Emmett is writing an article for an online music magazine on why some bands last longer than others. While researching the article, he compiled information about how long various bands last without changing their lineups. So if you know people who have like a rap duo, form a band, or you've been to some concerts, or know people who are in a band, that's pretty much it. One comparison he looked at was between the numbers of members in each band and the number of each year each band have lasted. So we all know that bands don't last forever. So all you do is take in this table, give me the regression equation, and to create the model. And when you do that, you should get, and remember your answers to be the nearest thousandths, should be that. And I almost forgot the X. I did not include the X on there, so you would include the X for me. So it's because it's linear, because this is linear, because when you put this in decimals and you type in the linear function, your R is going to be, if it's not going to be a -1 or a +1, you're going to come close to either or. So because of that, it's a linear. And it's going to be -2.849x. So again, all you do is just give me the regression model. Alright, so to my sports people, a table shows the heights of a football at various times after a punt. So yes, when you play football, people are recording how far you kick the ball when you do it professionally. And there's just, I guess, to have some type of record how hard you could kick or something like that. Feel free to correct me wrong, sports people. Now we gotta create the model of the situation. So when you put this in decimals, I could guarantee you this is going to be a quadratic, because your R squared is going to be either a perfect one or it's going to come dangerously close to being perfect. So you should have a model that looks like this. Your A is -16, your B is 70, and your C is 3. Alright? So a cup of soup is left on the countertop to cool. The table below gives the temperature in degrees Fahrenheit of the soup recorded over the 10-minute period. Write an exponential equation, and I'm telling you it's exponential to save you the torture of trying to figure out if it's linear, quadratic, or exponential, and you're going to round it to the nearest thousandths. So when you put that in, knowing that it's exponential, your equation should be this. So again, that's all you're really doing. Now, be aware, you're going to be doing some big old data sets. And data sets just mean all the numbers that you have collected. All right, all the numbers you have collected. Now, you got to analyze the regression. You got to talk about what does it mean. So we know what it doesn't mean for correlation. We do know that. We know that a correlation tells us about the strength of a relationship. Now we're going to talk about the equation. What does that mean for us? So here is a final example. Kiki works at Chick-fil-A on drive-thru. With calculating her taxes and deductions, her model for her coin or her money is y equals 1325x minus 63. So For every hour she works, she makes $13.25. And that's just me analyzing the situations given. That was the equation that we come up with, and I'm just analyzed it. All right. So here's the situation. The owner of a bicycle store wonders if employees who have take the longest break will also make the fewest bicycle sales. One day he noted that the length for each person's lunch break is minutes, as well as the number of bicycles he or she sells that day. Here's the regression. All right. So now we got to take this regression, the equation, and now we got to analyze it. So what can we say about it? Well, we know the slope is negative, you know? So we have a negative slope. So when we have negative slope, what's going to happen to my graph? I'm going to give you a moment to think about that. You almost ready? So, because the slope itself is negative, that means that if we were trying to compare the relationship, x and y, x being the minutes, so the more minutes he or she sells, the the longer the lunch breaks, which is the x value, that means that the number of bicycles is going to decrease because of the slope being negative. So now we already made the statement. Now let's go look at the fine details. So we analyzed it. So now we're putting it in the situation. If a salesperson spends 1 additional minute at lunch, our equation meaning 1, I forgot the S, to get rid of the S, my bad, predicts he or she will sell 0.272 or 272,000 fewer bikes that day. So that's just a prediction. So that's all you have to do. All right. So here, now we're getting past linear. Now we know that this is a quadratic because it tells us the following day represents the average minimum and maximum temperature recorded in the month of Raleigh, North Carolina over a 6-month period. The temperatures are recorded in degrees. Find the quadratic equation that best model the data and predict the minute temperature when the maximum temperature is 90 degrees Fahrenheit. So to do that, put in decimals, give me my model. There goes my model right there. So you're going to take 90 and plug it into every x you see, and you should get the answer of 70 degrees. So when you get 70, now you got to say our model is that, which tells us that the minimum temperature of 70 degrees will happen when the temperature is 90. All right. So yeah, you are dealing with the population. So we know anytime we're dealing with population or something that grows fast, you're dealing with exponentials. So a population of a single cell organism was grown in the petri dish over a period of 16 hours. The number of mechanisms have been recorded in the table below. Determine the exponential regression model for the data. Run the oddity values to the nearest 10,000th place. Use the equation to predict the number of single-cell organisms to the nearest whole number at the end of the 18th hour. So when you put this in Desmos, you're going to have a equation like that. And then to find out at the 18th hour, just put 18 in for the x that you see, and you should get something like this. And do not forget, y'all, because you're dealing with real world situations, you can't just give me a number. That would no longer work. You have to give me a full blown out situation. It is predicted, because you have to talk like that, that the number of a single cell I can't talk today, this evening rather. And here we go. It is predicted that the number of single cell organisms to this nearest whole number at the end of the 18 hours is 341.